Um, okay, today we are looking at ordinary differential equations, and we are going to be solving these questions that I have here. And you only need like an introductory information, basic information about ordinary differential equations. So we are going to go through these questions, and I'll be expanding more on the key principles for each and every question. So basically, we know that an ordinary differential equation, ordinary differential equation which represents as OD, represents as ODE. This is any equation which contains derivative. This is any equation. This is just any equation which contains derivatives. Okay, so when you're looking at this question, we start with question 1a. It says define the order of an ordinary differential equation and given an example for a fourth order ordinary differential equations. Okay, so we are looking at an ordinary differential equation. They are saying we should define the order of an ordinary differential equation. We know that we are looking at question 1a. So question 1a wants us to define the order of an ordinary differential equation. So the order of an ordinary differential equation is the largest derivative present in the differential equation. This is an order of an ordinary differential equation. This is the largest derivative present in the differential equations. So if you are looking at an example of a fourth order ordinary differential equation, we can have let's say we have 1 minus x squared d4 dy dx 4 minus 3 dy dx is equals to 0. So this is an example of an fourth order ordinary differential equations because the largest derivative present is the fourth derivative, isn't it? So this is an example of a fourth order ordinary differential equation. So this is how we are basically looking how you can find an order of a differential equation. Just look at the largest derivative present. This is the largest derivative present. If maybe you're looking for a second order differential equation, we are going to design an ordinary differential equations whereby the largest derivative is what? The second derivative. For in our case, the question asked for a fourth order ordinary differential equation. So this is one of the example, but you can take any example because they say you just give an example, so you can design any ordinary differential equation as long as the largest derivative present is what is the fourth derivative. Okay, so we have defined an ordinary differential equation, and also we've given an example that was 5 marks. And then with question 1b, it says determine the particular solution of this differential equation given the conditions that are, we're given conditions, and then they said we should use variables separable method. So we are given this information, and also we are given the conditions. So we are tasked to find a particular solution for this differential equation. So we have, this is B. For B, we are given that dy dx is equals to e 3x e minus 2y plus x squared e minus 2y. So this is an ordinary differential equation that was given. Also, are given conditions. We are given our boundary conditions where we have x is equals to 0 and y is equals to 0. So whenever you're given boundary conditions, we need to find a particular solution. If we don't have boundary conditions, which means we are tasked to find a general solution. So, and they say we should use the separation of variables, isn't it? We're using the separation of variables method. So if we want to separate the variable method, first of all, let's simplify this. Before we separate, we need to simplify this. So we can, when looking at this, these are like terms, so we can factor out e minus 2y, and then we'll be left with e to the power 3x plus x squared, isn't it? So now we are going to pair all of the terms with respect to y on one side of the equation and all of the terms with respect to x on the other side of the equation. So this is with respect to y, so we are going to bring it this side. So we're going to have 1 over e minus 2y dy, and then we'll be left with this. So we'll be left with this e 3x plus x squared, and then we are going to multiply the denominator dx, right? So now we have, and we can simplify these to e 2y, because now the power is negative. So if we bring it to the numerator, the power is going to be positive. So this is e to the power 2y dy is equals to e 3x plus x squared dx. So now we have separated. So this side we have all the variables with respect to y, and this side we have, and that side we have all the variables with respect to x. So now once we have separated the equation, then you integrate both sides. So we are going to integrate e 2y dy is equals to the integration of e 3x plus x squared dx. And when you're looking at this, we are respecting this function with respect to y, this function with respect to x. So that's why it's important when you're separating variables, you make sure that every variable with every term with the y variable is one side, every term with the x variable is one side. So that's when you're differentiating, when you're integrating, we're integrating with respect to one certain variable. So we're integrating this side with respect to x, right? We are integrating this side with respect to y. So this is very important. Okay, so looking at this one, so this is what we have, right? So now we have to integrate. So we have to integrate in this part. If we're integrating e to the power 2y, we are going to get what? We are going to, if we integrate an exponential function, this is going to be e 2y over the derivative of the power. The derivative of the power is 2, isn't it? And then this is going to be equals to, if we are integrating this exponential function, is going to be e to the power 3x over the derivative of the power, which is 3, isn't it? Plus, if you're integrating this polynomial x squared is going to be what? It's going to be x cubed over 3, isn't it? Plus 3, which is an arbitrary constant. So now we have integrated this equation. So from here we apply the boundary conditions. We apply the boundary conditions to get C, which is the arbitrary constant. So we are given that x is equals to 0, y is equals to 0. So we come in up and substitute. So we're going to have e 0 over 2 is equals to e 0 over 3 plus 0 cubed over 3 plus c. And if you evaluate this, this is going to be e to the power 0, and everything to the power 0 is 1. So this side we're going to have half is equals to 1 over 3 plus c, right? And if you solve this, you're going to get c is equals to 1 over 6. So this is the arbitrary constant c, and then we come and substitute it here. So we are going to have e to the power 2y is equals to 2 over 3. So we have, this is 1 over 6, yes. So we are going to have we are going to have, this is over 2, so this is e 3x over 3 plus x cubed over 3 plus 1 over 6, right? So if I multiply both sides with 2, I'm going to have e 2y is equals to 2e 3x over 3 plus 2x cubed over 3 plus 2 over 6 is going to be 1 over 3. So now I can just write this as a single fraction, whereby I have e 2y. I'm just simplifying this expression. It's 1 over 3. 2e 3x plus 2x cubed plus 1, like this, right? And then from here, I want to make y the subject of the formula. So from here, I can introduce ln from both sides, right? I introduce ln of e to y, and also this is equals to ln of 1 over 3 2e 3x plus 2x cubed plus 1, right? So if I introduce ln on the left hand side, obviously we're going to bring this power down, so we're going to have 2y ln e is equals to ln 1 over 3 2x 3x plus 2x cubed plus 1. So this will be, ln e is 1, so you have 2y is equals to ln 1 over 3 2x this is 2e 3x, and then this is 2e 3x plus 2x cubed plus 1. So now therefore y is equals to half ln 2e 3x over 3 plus 2x cubed over 3 plus 1 over 3. So now we have found, this is our particular solution. This is our particular solution. So we were given this differential equation, these ordinary differential equations with the boundary conditions. So we are tasked to find the particular solution, and also we are finding the particular solution because we have the boundary conditions. So we are going to, and we're asked to use the separation by variables method. So we had to first of all simplify and then group this equation according to the two variables, which was x and y. So on one side we grouped according to y, and on one side we grouped according to x, and then we integrated both sides, and we integrated both sides with respect to y and respect to x, and then we found the arbitrary constant using the boundary conditions, and we found that it's 1/6, and then we made y the subject of the formula by simplifying the entire equation. So this is our particular solution. So moving to question 2, it says define nonlinearity of a differential. Define nonlinearity of a differential equation and give an example of a nonlinear third degree fourth order differential equation. So okay, with this one 2a, so we're looking at question 2a. So with question 2a, what is a nonlinear differential equation? So a nonlinear differential equation, this is a differential equation which contain the product of a function. This is a differential equation which contain the product of a function, say y of t, and its derivatives. So this is a nonlinear differential equation. We are saying it contains the product of a function. In our case, we can call it yt, and its derivative. So okay, so an example of a nonlinear differential equation can be, in our case, can be sine y d4y dx with derivative plus y squared d squared cubed is equals to 0. So this is an example of a nonlinear differential equation. So let's talk about a linear differential equation. We are saying a linear, before we come here, let's talk about a linear differential equation so that you can see what is a nonlinear differential equation. So when you're talking about a linear differential equation, this is any differential equation that can be written in the following form. So we have an of t, yn t plus an minus 1 of t, yn minus 1 of t plus it continues to a1 t y t plus a naught of t yt is equals to g of t. So it can be a linear differential equation can be written in this form. And the most important thing to note about a linear differential equation is that there are no products of the function. There are no products of the function y of t and its derivative. This is very important. So with the linear differential equations, especially in this format, we are saying one thing that you have to note: there are no products of the function yt and its derivative. That's the major thing. And the another thing we're saying, neither the function or its derivative occur to any power other than the first power. So these are the most important things that you have to note about a linear differential equation. But if you are talking about a non-linear differential equation, in order to get a non-linear differential equation, in our case, we were tasked to define a non-linear ordinary differential equation. So a non-linear differential equation, it does have a product. So it's sort of like the opposite of a linear differential equation, because we said this one contains the product of a function y and its derivative, but with the linear there's no product. So that's how you can define a non-linear differential equation. And also this example, this is the function y of t, right? This is a function y of t and its derivative, and they are a product. This is the product, you see. So that's why we are saying this example is an example of a non-linear. This is an example of a non-linear differential equation. And also we are saying the function y of t or its derivative occur only to the first power, right? But here we can see that the function of y is at the second power, so that this makes this entire equation a non-linear differential equation. So this is an example of a non-linear differential equation. That our question said we should define non-linearity of a differential equation and find an example of a non-linear third degree fourth order. So third degree, this is a third degree. So this is the third degree of our equation. So this is the third degree. This is a third degree, which is the power of the derivative, the power of the second derivative, the third degree. And also the fourth order, which means this is the largest derivative in this non-linear differential equation is the fourth derivative. So this constitutes of the third degree fourth order non-linear differential equation. So question B says okay, now we are tasked to, question 2b, we are tasked to find the particular solution of the following ordinary differential equation. We are also given an ordinary differential equation with boundary conditions. These are the boundary conditions, and they are saying we should use the integrating factor method. And the previous question we are using the separation of variables. Now we are using the integration factor method. So the integration factor method, we are given, so here we are given that we are solving B. So we are given that 1 plus x dy dx minus 3y is equals to x plus 1 to the power 4. And we are given our boundary conditions to be x is equals to 0 and y is equals to 1. So if we are using the integration method, we need to rewrite this equation into a certain format, whereby we need to write it in this format, whereby you're saying dy dt plus p of t y is equals to g of t. So we are going to rewrite this equation in this format first before we can do anything else. So now we can see that the coefficients of dy dt, the first derivative, it's 1. So we need to make sure that the coefficients of dy dx is 1. So we are going to divide each and every term by what? By 1 plus x. So we are going to have dy dx minus 3 over 1 plus x y is equals to x plus 1 to the power 4 over 1 plus x. So we can simplify this, right? Because this is to the power 1, this to the power 4. So this is going to be 3, isn't it? So we can rewrite this simplified form of this one to be, we can say this one is equals to x plus 1 cubed. So now we have written this equation in this format. So from here we need to determine the integrating factor. So our integrating factor u of x should be e. U of x should be e to the power. Should be e to the power the integral of p of x dx. So this is how we find the integrating factor. So in our case here, we can see that this is what? This is p of t, right? And then this is g of t. So our u of x is equals to e to the power, the integral of p of x is going to be what? Is going to be this 3 over 1 plus x, right, dx. So now we have found the integrating factor. So let's simplify it. Nu x is equals to e, the integral of, or it's minus 3, so it's minus here. So we have minus 3 over 1 plus x dx, and then this is going to be, if you find the integration, remember, if you integrate the denominator, the integration of k over k plus x, this is what? The integration of kx plus 1, this is ln kx plus 1, right? So it's the same thing here. So here we are going to have, if we integrate this, we are going to have minus 3 ln 1 plus x. Because remember, if you integrate, the formula is like this: the integration of f dash x of f of x dx, we are going to get what? Ln of f of x. So which means this is going to be e to the power minus 3 ln 1 plus x. So now our integration factor u x is going to be equals to e minus 3 ln of 1 plus x. And then from here we can simplify this to be, this can actually be this can actually be ln, this is, okay, let me just rewrite this as e to the power ln plus x to the power minus 3, because we can take this power using the power rule. We can take this negative 3 to be the power of 1 plus x, isn't it? So from this point we can just get that this is 1 plus x to the power minus 3. Remember, e to the power ln of a, this is the same thing as a, so this is what I've applied here. You should know e to the power ln of a is the same thing as a. So from this point we have our integration factor. So nu of x is equals to what? Is equals to 1 plus x to the power minus 3. So then what do? We multiply this equation. We multiply this equation with the integrating factor. So we're going to multiply this equation with the integrating factor. We are going to have with the integration factor, we're going to have 1 plus x minus 3 multiplied by dy dx, right, minus 1 plus 3 minus 3 times we're going to multiply times 3 over 1 plus x y is equals to, we are multiplying every term with the integrating factor. So this is x plus 1 and 3. So now let's simplify this. If we simplify this, we are going to get, so looking at this one, if we simplify this, is with 1 plus x dy dx. If you simplify this term, we are going to have minus, this is minus 3. If we bring this denominator to the numerator, it's going to be 1 plus x minus 1. So which means we're going to get 1 plus x minus 4, because here we're going to have 1 plus x minus 3 times, if you bring this denominator, we are going to have 1 plus x minus 1. So same base, you add the powers, and it's going to be minus 4y. This is equals to, and here same base, you add the powers, minus 3 plus 3 is going to be what's going to be 0. So 1 plus x to the power 0, it's what? It's 1. So now we have this one. We have this, this 3. We forgot the streets here. So now when you're looking at this one, this is the same thing as the product rule. Because this is uv plus vu, right? So here this is our u, this is our v, right? And then this is our v dash, and then here we have our v, this is our u dash, because if we are taking this, well, this is to the power negative 3, because we are multiplying by the integration factor. This is part 1 plus x to the power negative 3. If this is u, right? So if you differentiate u, if you differentiate 1 plus x to the power minus 3, you're going to get what? If you differentiate this, you're going to get minus 3, 1 plus x, and then you're going to minus 1 here to be minus 4, which is the same thing as this, right? So this is the product rule. So also if we have v, if we have y, if we differentiate y, you're going to get what? Dy dx. So from here we can see that the left the left hand side of this equation is the product rule, so we can write this as u v dash. So this is our u, this is our v. So we are going to have u is going to be 1 plus x minus 3 times the v is going to be y dash. This is equals to 1. So when you have reduced it to this form, we can then integrate both sides. We integrate both sides. 1 plus x minus 3 y dx. This is equals to the integration of 1. So integrating 1, this is dash. So if we integrate if we are integrating u v dash dx, this is the same thing as uv. We're just going to get uv. So this is going to be y times 1 plus x minus 3 is equals to integrating 1. We are going to get what? We are going to get x, and then plus the arbitrary constant. And then if you apply, and then from here, if you apply the boundary conditions, you are given the boundary conditions to be x is equals to 0 and y is equals to 1. So if you apply them here, you are going to get 1 plus 0. 1 plus 0. 1 plus 0 minus is equals to 0 plus c, and therefore c is going to be equals to what? C is going to be equals to 1. And then we can rewrite this as y 1 plus minus 3 is equals to x plus 1. And then if you make y the subject of the formula, you are going to get x over 1 plus x minus 3 plus 1 over 1 plus x minus 3. And since it's minus, we can bring it up as the numerator to be positive. So this is going to be x 1 plus x minus 3 plus, it's going to be positive now because it's brought it to the numerator. It's going to be positive, so this is going to be x plus 1 positive 3. And then you can factor out these 2. You are going to have x is equals to, if you factor out 1 plus x cubed, you're going to be left with what? X plus, if you factor out plus 1 here, so this is going to be y is equals to 1 plus x cubed, x plus 1, and finally this is y is equals to x plus 1 to the power 4, because this is to the power 1, so 3 plus 1, it's 4. So this is our particular solution for question 2b. This is our particular solution for question 2b. We are tasked to find the particular solution using the integration factor. So we are going to do number 3. So with number 3, it says for what values? It says for what values of m will this be a solution to the following ordinary differential equation? Do not solve this equation. So that is very important. It's 5 marks. We are given this equation. Okay, so how do you work about this one? Question 3. So we are looking at question 3. Question 3a. So we are given that y is equals to e, y is equals to e mx. So we're given d squared dx squared minus dy dx minus 2y is equals to 0. So coming back to the question, it is very important. They are saying for what values of m, so we are looking for the values of m, will this be a solution to the following differential equation? So what are the values of m such that this will be a solution to the ordinary differential equation? And we are given the ordinary differential equation, and they are saying we do not solve this ordinary differential equation. So what we are going to do here, we are going to take this trivial solution, y is equals to e to the power mx. We're going to take that trivial solution, and then you're going to differentiate it twice and substitute it here and here and here and find the values of x. So this is also a way of finding the auxiliary equation. If you are not using the d operator, you can also use this principle to find the auxiliary equation. So we are assuming that, so we want to know when will this be a solution. What are the values of m that will make this function to be a solution to this ordinary differential equation? So the first thing that you do, you find the first derivative of this trivial solution. This is a trivial. This is a trivial solution. So we are going to find the first derivative, dy. Sorry. Okay, what happened? Okay, so we are going to find the first derivative of this trivial solution. So we are going to have dy dx is equals to m e mx. That's the first derivative. And then we are going to find the second derivative, dy dx squared is going to be m squared e mx. And then from here we have dy dx, we have the second derivative, we have y. We are going to substitute everything in this equation. So dy dx, the second derivative is going to be, it's m squared e mx. This is the second derivative, minus the first derivative is what? This is the first derivative here, is going to be m e mx minus 2. What is y? Y is this, which is e mx. This is equals to 0. So we differentiated this trivial solution twice, and then we substituted the derivatives in this second order differential equation that we were given. So from this point we can factor out the common term, which is e to the power mx. E to the power mx will be m squared minus m minus 2 is equals to 0. And therefore from here we can see that m squared minus m minus 2 is equals to 0. So if we solve this quadratic, we can get that m1 is equals to 2 and m2 is equals to -1. So these are the values of x. These are the values of m that will make this function to be a solution of this this second order differential equation. So also this is actually the auxiliary equation for this second order differential equation. So we can also use this method to find the auxiliary equation for this second order differential equation. So now this was a, this is how we find the values of m. So equation B for 3, it says find the particular solution for the following differential equations given the conditions. We're given the boundary conditions to be this. Okay, so we are given if we are solving this one, so we are given that dx squared plus 5 dy dx plus 6y is equals to 0. So using the d operator, we know that d squared is equals to d dx squared and d is equals to d dx, right? So from here we can rewrite this as d squared y plus 5dy plus 6y is equals to 0. And then if we factor out y, we are going to have d squared plus 5d plus 6y is equals to 0. So from here we can deduce our auxiliary equation. So from this equation, where there is d, we just substitute it. Where there is d, we substitute it with m. So m squared plus 5m plus 6 is equals to 0. So this is our auxiliary equation. This is our auxiliary equation, and this is how we solve a second order differential equation. This is a second order differential equation. So when you're dealing with a homogeneous second order differential equation, it's homogeneous because it's equals to 0. So if you're dealing with the second order homogeneous differential equation, we need to find the auxiliary equation first, and then once we find the auxiliary equation first, we find the values of m. So m is equals to -2 or m is equals to -3. Depending on the textbook that you're using, some can use m is just a variable, some can use lambda or whatever variable. So but this is the basic way of going about it. And then from here we can, when we're using, after we find the values of m, we have to construct our cumulative function, which is going to be y. Since we have two distinct values of m, which means our function is going to be a is equals to e minus 2x plus b is going to e minus 3x, since our values of m are distinct and they're different. m1, this is 1, this is 2. m1 is not equals to m2. If m1 is not equals to m2, the function is going to be a, which is a constant, is equals to e m1x plus b times e is equals to m2x. So this is the function that we use. But if m1 is equals to m2, we have y is equals to ax plus b, and this is equals to just m. This ax is equals to e mx. This is what you get if there are two. Okay, in our case there are two distinct values of x, so we are going to get our function to be this. So from here we need to apply the conditions that we are given. So we are given our boundary conditions. We are given our boundary conditions to be x is equals to 0 and y is equals to 0. Also dy dx is equals to 1. So let's just apply. We're given x is equals to 0, y is equals to 0, and dy dx is equals to 1. So let's start with let's apply these ones first from here. So y is equals to 0 is equals to a e minus 2 0 plus b e minus 3 0. So from here you have 0 is equals to a plus b. Therefore we can see that a is equals to minus b. So this is the first equation, and then now in order for us to also apply this one, you need to differentiate this one, right? So if we differentiate that one, you're going to have dy dx is equals to minus 2a e to the power negative 2x minus 3b e to the power minus 3x. So from here we can also apply these boundary conditions. Dy dx is equals to 1, which is equals to minus 2a, and then e to the power negative 2 0 minus 3b e to the power negative 3 0. So if you simplify this, we are going to have minus 2a minus 3b, right? So here, so from this we can just so from here we substitute, because we know that a is equals to minus b. Where there is a, we substitute minus b. So 1 is equals to minus 2 minus b minus 3b. So if we solve this one, we are going to get that from here we can see that we're going to get that b is equals to minus 1. So we know the value of b is equals to minus 1. So in this equation where there is b, we substitute minus 1. So a is equals to minus 1, which is equals to 1. So now we have found our arbitrary constants a and b. B is equals to 1, b is equals to negative 1, a is equals to 1. So from here we can rewrite our function to be y is equals to e to the power minus 2x minus e to the power minus 3x. Remember, this was a 8 minus 1 here, b is, well, a is 1 here, b is minus 1. So this is our function. So this is the particular solution for this question. So this was question 2. This was question 3b. So we had to find the particular solution, and then now we are looking at, okay, so on the next video I'm going to do question 4, but with question 4 we are just looking at particular integrals, and also looking at non-homogeneous ordinary equations. So I'm going to do question 4 is 25 marks, and it's 4 marks. This one is 4 marks, this one is 25 marks. So stay tuned for the next